Fine. So what are we going to study? Basically we are going to study stellar structure and later on various aspects of stellar evolution. Okay. Now to start with, let us first talk about the simplifying assumptions. Okay, these are very important, and later on as we keep on moving in our course, at times we will relax them so as to achieve better fidelity to observations. Now the first and one of the most important assumptions on stellar structure is spherical symmetry in stars. Now of course this spherical symmetry here, this is prompted by self-gravity and is a very good approximation for most of the stars. But it doesn't mean that there are no deviations. Of course, we can have deviations from spherical symmetry if non-central forces become important relative to gravity. And what are they? Two most important reasons are rotation and magnetic fields. Now, although many stars are observed to have magnetic fields, the field strength. So you see, we are talking about spherical symmetry, right? Yes. Now what I am saying is that there can be two reasons for violation. So violation reasons. One is rotation and another is magnetic field. Okay. Now although many stars are observed to have high magnetic fields, say for example a highly magnetized neutron star, but still you see the field strength for such stars inside them is always negligible compared to gravity. Now what about rotation? Rotation can be more important, and in fact rotation rate, you see this rotation rate can be in fact considered an additional parameter besides mass and composition, which determine the structure and evolution of a rotating star. This is not a part of your course, although I will talk about the structure of a rotating star in the advanced class, but it is important to know that such things are there. Okay. Now, so for the majority of stars, say for example our Sun, the forces involved are small compared to gravity, and indeed we can have the very good approximation of spherical symmetry. Okay, good. Now the next assumption is isolation. Now what does this mean? Of course this means that stars are isolated in space. Now, why do we do that in the first place? We are considering them to be isolated in space so that their structure and evolution depend entirely on the intrinsic properties, that is mass and composition. So if two stars are quite close to each other, what will happen? Then the intrinsic properties like mass and composition, which is denoted by xi, of one star could depend on other star as well. And this you will see when I talk about binary star system. Binary star system, you will see that such a thing happens, and at that time we can no longer talk about isolation. But for most single stars in this galaxy, this condition is satisfied to a very high degree. Say for example our Sun. You can just check it by yourself by comparing the dimension of the Sun to that of the distance of the Sun from Alpha Centauri, okay, which is the nearest star, closest star to Sun, and you can easily see that this distance is very much lower than the dimension of the Sun, even the dimension of our solar system. Okay. However, note that for stars in dense clusters, similar to that of binary star system, we cannot use this isolation feature approximation. Okay, because in that case, for dense cluster where there will be many stars, in that case what will happen is that the evolution will be influenced by the interaction with neighboring stars. In the binary system we only have two stars, but in the cluster we will have like many body interaction, many star interaction. Fine. Now of course we will ignore all these things for the time being. So this is so for the time being, for single star system this is okay, right? Fine.
Sir?
Yes.
স্যার বলছি যে এখানে যে আইসোলেশনের কথাটা বললেন স্যার, তা ওইখানে কোন স্টার আরেকটা স্টারের থেকে মানে কতটা দূরে থাকলে আমি বলতে পারবো যে এটা আইসোলেশন আছে?
Fine. First I will talk about it later on. In the binary star system, when I talk about it, there is something called Lagrangian points. Okay, Lagrangian points, Roche-Loeb, mass transfer. Actually, you see, when I am saying that the mass of one star and the composition of one star will be affected by the other, what I mean is to say is that the mass of one star can be, there is a possibility that it can be transferred to the other star. But how will it happen? There are stages in the evolution of the star where such a feature can happen. And we will talk about it in more details when I talk about the Roche-Loeb scenario, Lagrangian points, later on. But first I will have to talk about stellar structure, then evolution. Okay? Then only you will understand how a star can lose its mass to a nearby star. And then at that time I will answer your question of how much the distance will be. Okay? Okay, okay. Good question. জিজ্ঞেস করবে, কোনো অসুবিধা হলে জিজ্ঞেস করবে। Now, the third very basic approximation is this one, which is uniform initial composition. Now, stars are formed with a very homogeneous composition. What I mean to say, this is a reasonable approximation. Why? Since the molecular clouds of which they are formed are well mixed. Now, in most of the case, you will see that we will assume a quasi-solar composition. And what is that? This is capital X is equal to 0.70, capital Y is equal to 0.28, and capital Z is equal to 0.02. Now what is this? What is this capital X, capital Y and capital Z? Something is there, right? You see, it has been observed that in the interstellar galaxy, most of the stars, they comprise mostly of hydrogen. A very small amount of helium, helium is there, and very small amounts of other metallic elements, And here we are denoting hydrogen, the composition, how much is there, the percentage, mass composition, right, of hydrogen by X, helium by Y, and other elements apart from hydrogen and helium by Z. Okay? Fine. Now in reality, there is a relatively little variation in composition from star to star, so that the initial mass is the most important parameter that determines the evolution of a star. Okay. So these are the three most basic assumptions. Now in fact there is a fourth assumption of LTE, local thermodynamic equilibrium. I will talk about it, but just remember that apart from these three, there is a very fourth important approximation as well, and this plays a very important role when we talk about the radiative energy transport in stars.
কম্পোজিশনটা এবার
হ্যাঁ
হাইড্রোজেন স্যার মোস্ট অফ দ্য প্রবাবলি প্রথমে হাইড্রোজেনটা ফিউশন করে হিলিয়াম হয়, হিলিয়াম থেকে সেটা আবার আর অনেক সাইকেল আছে, সিএনও সাইকেল, নাইট্রোজেন হলো, পরবর্তী হেভিয়ার এলিমেন্ট গুলো তৈরি হয়। তো স্যার এর ব্যালেন্সটা কি তাহলে স্যার এটা ইউনিফর্ম কি করে থাকছে? মানে স্যার ওটা তো চেঞ্জ হচ্ছে স্যার কম্পোজিশন।
Yes, composition will keep on changing. I am talking about a very initial. This is basically a quasi-solar composition. So this means that initially there was much more hydrogen. Later on, when hydrogen was, this is not the initial part. You see, this is just an approximation of a model. Initially, there was almost say more than 90% of the hydrogen. Now, some of it will be converted to helium. Okay. This is not the initial part, and this is just a quasi-solar composition by name. When you will see, I will talk about various other types of composition and how the composition changes. If time permits, today we will talk about it. They are the very important set of dynamical equations for stellar structure known as composition equations. Okay. Any more question? Okay. If none, then let me proceed to the next part. Okay, you see, with this assumption of spherical symmetry, now let us talk about the equation of continuity or mass conservation. Yes, so as I was saying, you see, with the spherical symmetry, we can now describe the physical properties of stars as a function of radius, distance r alone, distance from the center here. Now, one of the properties is the mass enclosed within a radius r, small r. This is a small r, and this is the center, and this is the entire star whose mass is capital M, star mass. Okay. Now you see, these we can readily obtain these two properties considering the mass enclosed within the radius r, right? So mass as a function of r. So these are two equations. Note that it is frequently more advantageous to use m instead of r. So what I am saying or proposing is that let us use mass m instead of radius or distance from the center r as the independent variable. And why? Since mass is bounded in the range. And what is the range? The range is this, where capital M, of course, is the total mass of the star. Now, during the entire course, remember, during the entire course of a star's life or its evolutionary phase, the total mass may decrease slightly due to stellar winds, which means mass loss. But there is not a wide fluctuation in that. On the other hand, the radius of the star will vary by several orders of magnitude during this time, while there is a very minimal change in mass. You understand? What I am saying is there is very slight change in this mass during the entire evolutionary phase, whereas the radius will be changing by a lot, by orders of magnitude. So it is better to use this as an independent variable. Now, as I was talking previously here, you see, regarding the fourth approximation, which is the local thermodynamic equilibrium. What does it do? Basically, this allows us this approximation. Now, what is local? I will talk about it in details later on, but just let me give you a very small glimpse. Now, this fourth approximation, this allows us to calculate all of the thermodynamic properties in terms of the temperature T. Now remember that thermodynamic equilibrium implies that all interactions and processes happen at the same rate as the inverse processes. So What is local thermodynamic equilibrium? Now, local thermodynamic equilibrium is achieved when the mean free path of particles in the gas. So, when is it achieved? You see, it is achieved when the mean free path of particles in the gas is much smaller than the length scale for the temperature change. And in fact, the composition of star is described, as I have previously told you, as by mass fractions, xi. Okay, now sometimes we used xi in general term for mass fractions and x for hydrogen, specifically y for helium and z for other elements. Now, so with these four basic assumptions, we have talked about this. We have just sort of derived this equation of continuity or mass conservation. Now, this is a very basic equation. Fine. Let me now talk about the energy equation. Now, you see, the energy equation for stellar structure is obtained by considering a very small mass element dm over here, that is in a spherical shell. Again, this is a spherical shell over which the temperature T, density and composition are considered constant. Okay, so in this shell we will consider these three quantities to be constant. Now we also need some other variables as well, parameters. Now let the internal energy per unit mass in this shell, we are now talking about shell only. Okay, so out of the entire star, we are now trying to discuss the microscopic physics of this shell. So, physics of shell. We talked about temperature, density and composition being fixed. Now, let me again say that the internal energy per unit mass in this shell be U. Then we also have pressure P and volume V in this shell. Now, let us apply the first law of thermodynamics, according to which, you remember, any changes in the internal energy are related to the heat added and work done through one of the most basic equation. Now, let me write down this equation here. So this is one of the most basic equation, right? Now what about the work done? How much is it? This is the amount of work done. Okay. Now remember, these two equations, I have named them 1 and 2. So let me name these two equations by 3 and 4. And this is basically the work done. Okay, fine. Now here we have used basically dm by dv, this is important to note, as rho. And also note that the thickness of shell is defined in terms of dm. Interesting, right? Not dr. And of course it can be considered constant, although dr may vary as the internal energy and the work change. Fine. Now you see, the heat added here, the heat added can come from the release of energy in the gas here, usually from the nuclear burning, or from an imbalance between the heat added and heat removed due to flux through the stellar envelope here. For the time being, let us denote Q as the nuclear energy release per unit mass, and Fm as the heat flowing through the spherical surface. Okay, defined by the mass m here, this one I have just denoted. You see Fm over here, you can see. Now at the surface of the star, what do we have? So at the surface we have small m is equal to capital M, and this thing, you see, F of capital M equal to L, which is luminosity. So the heat added is the change in these quantities over a time period of delta t. And how much is it? It is this amount. Let me rename this as equation 5. Okay. So now from the definition of derivative, we have this thing, you see, this follows from the definition of derivative, and as a result we can write delta Q as this form. This is equation 6, this is equation 7. So finally we will have this combined relation, which is equation 8. I am just playing with the first law of thermodynamics in the star and trying to see what effect is there. Okay. Now let me divide this by delta T. This delta T, and convert the quantities delta by delta T to time derivatives. Then we will have the energy equation. This is the energy equation. It follows from the previous equation using these two things. So basically this is a result of the application of first law of thermodynamics in the star. Note that this equation is valid even when the star is evolving, energy equation. Okay. Even when star is evolving. Now, if the star is thermally stationary or thermal equilibrium, then we assume that the quantities do not vary with time, which means that u dot will be equal to 0 and delta dot, all the dot stuff will become equal to 0, and in that case the energy equation will become what? It will take a much simpler form. You can see from the previous equation. Yes, you see, from this form we will get just this thing. This is equation 10. And what about the nuclear energy generation rate? Well, the nuclear energy generation rate, it will be basically this quantity. Now you see, what did we observe? As we have been expecting, we observed that the luminosity of the star in equilibrium is equal to the nuclear energy released in its interior. Okay? So, we have just now derived two equations. The first one was the equation of continuity or mass conservation, and the second one is the energy equation. This one over here. Fine. Any questions till now? Okay. So till now we have discussed and also derived the two equations. The first is the equation of continuity and the next one is the energy equation. Okay. And this is the third equation or the hydrodynamic equation. And here in this diagram you can see the forces acting on a volume element of mass dm. This is the mass of the volume element in the interior of the star. Okay. And also, why are we considering this? Because we will be deriving this very important hydrodynamic equation, which is in fact a part of a much more important equation, or known as the equation of motion. So, the volume of this small mass element is dV, which is dr into ds. The ds is the surface area element at radius r. ds surface area element at radius r. And also this is the mass. Note that we are not using dm. We are not using dm. Why? Because we are not looking at the mass of the spherical shell. Now, what are the forces which are acting on the mass element? You see, there are two important forces acting on the mass element. The first is the gravitational force, and the second one is the pressure force. Here, P or the pressure is not a function of theta or phi. Why? Because we have imposed spherical symmetry. Now, just like the previous case, using the definition of derivative, we will now expand pressure, and as a result we can write this. You see, if we write this P at r plus dr in this form, then we can write these two equations. Now this is equation number 12, continuing with our previous numbering, and this is equation of number 13. This thing. Now, as a consequence of gravitationally driven systems, the mass of the mass element can be divided out over here, and as a result we will just have this equation. Equation number 14. Now let me again do some change. Since we prefer to write everything in terms of m rather than r, so we have to do this change. However, do note that dr is dm divided by 4 pi r square into rho, and so if we incorporate this, we will have a similar equation, but in terms of del m, yeah, and this is equation 15. This equation, you see, this important equation, this is also known as the equation of motion. And this equation describes the time dependent systems that may be out of equilibrium, and they can be expanding or contracting. Now only in case of equilibrium the r dot is equal to 0. So in equilibrium r double dot equal to 0, and then we will find from this equation of motion the equation of hydrostatic equilibrium, which is this equation, and numbering is 16. So this is the HE equation, or equation of hydrostatic equilibrium. Okay, any questions till now? None. Fine. So let me just save this first. That's it. Yes. Okay. So now you see, next we are considering the composition equations. And since we know that stars shine by nuclear fusion, so this means that the composition xi, it changes with time, and this has an important impact on the structure of the star, where the nuclear fuel is slowly used up and as the internal pressure changes. So let us first consider the center of the star being made up of ideal gas, and here the pressure is P and temperature T. So we can write down the ideal gas law, where K is the Boltzmann constant. Now if the initial composition is hydrogen, and after time all of the hydrogen has been converted to helium, the mass of the gas particles, which is mg, has quadrupled, right? How? Because we have 4 hydrogen forming helium, basic reaction, plus energy. Now in order to maintain the pressure needed to support the outer layers of the star, over here, outer layers, the density or the temperature must increase. Thus the evolution of the stellar composition contributes to the evolution of the structure of a star. Now as I have previously told you, we describe the composition of a star in terms of mass fraction of each nuclear species. Example, hydrogen, helium, and so on. And this mass fraction is defined like this. Okay, where this rho I, what happened? Yes, where this rho I and rho, these two are the bulk densities in some region of the star. Now frequently when describing bulk composition of a star, we sometimes use capital X, as I was telling you before, capital X as the mass fraction for hydrogen, capital Y as the mass fraction for helium, and then we lump all the other elements into a category of metals and name it by capital Z. This is just a sort of nomenclature. The number density of a given species is then given by Ni is equal to rho I by small mi. Now this is equation 18 and this is equation, this is rho I. This is equation 19. Here this Mi is the mass of one nucleus of the given species. Now you see, to a good approximation, we can write the mass of one nucleus as the sum of the masses of its nucleon, which means we can write it like this. This is just an approximation again, where Ai is the baryon number and Mh is the, here Mh is the 1/12 of mass of 12 carbon atom nucleus, 12 carbon nucleus, 1/12 mass of 12 carbon nucleus. Thus, what do we have regarding Ni? Thus we have Ni is equal to rho I divided by Ai into mass of hydrogen, equation 21. So we can relate Xi and Ni using the following relations. These two relations. You can check this by yourself as well. Let me name these equations. Equation 22 and 23. Okay, so now let us start with the nuclear game. Well, nuclear processes inside stars, we do know what they do. They result in changes in Ni here. At the same time, the rate of nuclear reactions depend upon Ni as well as the temperature. In general, you see, a nuclear reaction consists of what? Two nuclei combining to create two different nuclei. So, let us denote I, Ai, Zi and J, Aj, Zj to be the reactants with baryon number A. Reactants, these are reactants having baryon number A and nuclear charge Z. Similarly, the products of this reaction are given by K, AK, ZK and L, AL, ZL. Okay, then in this case we are considering a two-body reaction. Okay, then in this case this reaction is described like this, equation 24. So we are going to talk about this very basic reaction. Now this is subject to the baryon conservation, of course, which is Ai plus Aj equal to AK plus AL, and charge conservation, which is Zi plus Zj equal to Zk plus Zl. Okay, now several reactions will also include neutrons, electrons and positrons. Neutrons and protons are part of, we know what is the part? They are baryons. Similarly, positrons and electrons are part of leptons. Now, leptons are also conserved. So, whenever a positron or electron is produced in a reaction, additional leptons, known as what? Neutrino, must be produced in order to conserve the lepton number. Also note that this reaction can go in both ways. Symbol here, it is not equal to, it is a both way symbol over here. Okay, fine. Now, in order to obtain an equation relating the time evolution, this is our aim. Okay, so our aim is to obtain an equation relating the time evolution of the composition of the stars. So for that we need to look at the rates of the nuclear reaction. Now, from terrestrial experiments using a beam of nuclei fired at a target, we can measure an effective cross section for a reaction using this relation. You see, sigma E, which is the total number of reactants per nucleus per unit time, divided by, you know this definition, number of incident particles per unit area per unit time. We know that this cross section has the units of area, and it can be thought of as roughly the cross-sectional area of the target particle to incoming particles of energy E. Okay, so we have talked about cross-section. What next? Now, to find the reaction rates in units of reaction, so we have to find reaction rate in units of reactions per unit volume per unit time. What do we need? So for that we need to consider the number of particles that will hit a target of cross-sectional area sigma E, assuming that all the particles are moving in one direction. Okay, so let X be the target particle, X target particle, and I denote the incident particle. Now suppose the gas we are considering, it is described by Maxwell-Boltzmann statistics. Then we can write it down like this. The NE expression, this is our well remembered expression, okay, where this NED is basically the number density of particles having energy between E and E plus dE. Okay, so what next? Now the number of reactions. You see what we are doing. Let me show you this diagram, then it will be more clear to you in this what we are doing. This diagram, you see this is what we are talking about, particles moving in one direction. Now the number of reactions dNE, number of reactions dNE, what is it? It is the number of particles with energy E that can strike X in a time interval dt with velocity VE, given by root twice E by mi. Now this is the number of particles contained in the volume. What is the volume? And this is the number of particles contained in the volume. Sigma E, look into the picture, sigma E, V, E and dt. So we will have the number of reactions given by this expression. Equation 27. So this clearly follows from this diagram that we have shown. Note that here this quantity NIE is the number density of incident particles with again energies between E and E plus dE, which is a fraction of the total number of particles. So we have this relation. Right, and thus we have you see this relationship, equation 28, where this N and N and Ne, they refer to all particles in the gas, and Ni and Nie refer only to species I. So now finally we are ready to write down the number of reactions per target nucleus per unit time, T. So what is it? You see, the number of reactions per target nucleus per unit time per time interval dt, again having energies between E and E plus dt, is given by this expression. Now, this readily follows from our previous discussion equations. Note that since there are nx target particles per unit volume, so the reaction rate will be given by this beast, equation 30. Okay, so this is the reaction rate. Also note that here X, this X, is of one type of particle. As I, then we have counted each interaction twice. So once with the particle as target and once with the particle as incident. So the reaction rate, what will it be for identical particles? This is the general case, but for identical particles we will have a separate equation, and this is the case for the identical particles. Now we can simplify this equation by defining. আচ্ছা তোমাদের তো এখন ক্লাস আছে না? You have class I think, but I am almost there, just give me 2 more minutes. Now we can simplify this equation by defining this. Rijk, this term, which is of the order of I into V. Okay, we can have a simplification. Let's see, where these two terms, this and this, they are average cross sections and velocities, and the assumption is that Rijk governs the reactions. It governs the reactions I plus J forming K plus L. That is, L is implied by I, J and K and the conservation laws. Consequently, one can write the rate of change of Ni. We can write this in terms of now Rijk like this, which is equation 33. Okay, and this is equation 32. Here you see the first term describes the depletion of species I through the forward reaction, and the second term describes the increase in species I due to reverse reaction. Since the mass fraction is related to the number fraction. So we have finally we have this relation, equation 34. Now we can write this is the composition equation, okay, final composition equation, and we can write this as a vector with each component representing a different species. No, let me write it down differently. We have to use bold symbols basically. So we can write it like this, in this form. This is the equation 35. Now although this equation may seem unsatisfyingly vague to you, it is indeed the equation which governs the evolution of the composition of the star, and it is usually implemented in the stellar evolution using a table of known values of this Rijk. We must know this to compute them for each reaction. So what did we have finally? You see, till now we have a set of evolution equations. And what are they? So these are the final set of evolution equations. 36, 37 and 38. This one we have finally just obtained. Now, so this is the composition equation, energy equation, equation of motion. Now this set includes the unknown structure functions which are also there. Rho, mt, temperature, mt, and this x, which is a vector, again mt, that must be solved in order to describe the star. But it also contains other functions that must be supplied from additional physics. Say for example, thermodynamics and statistical physics will give us P and U. Similarly, atomic physics and radiation transfer will supply us F. And nuclear and particle physics will supply us this part. So, today's class is over. We will talk about next part in the next class.